Hello everyone, welcome to GNANA DEEKSHA, concept-based digital learning. I am Dr.P.Kavitha, degree lecturer in mathematics from TSWREIS, Nagar. Today, my session will be on mean value theorems. In this session, I will be covering the basic definitions of continuity, differentiability, and mean value theorems, its geometric interpretation, and also the applications of mean value theorems. Now, let us start with the definition of continuity. Now, mean value theorems. In this concept of mean value theorems, let us first see what is the definition of continuity. Let us understand the concept of continuity with drawing a figure. So, this is my x-axis, this is y-axis, this is the origin. Suppose I am drawing a curve like this. If you observe, this curve is not at all having any gaps in between. So, this type of curves are said to be continuous curves. Okay. Now, if I draw some other graph, something like this is x-axis, this is y-axis. If I am drawing a curve like this, you observe there are some gaps in between. So, these gaps, whenever these gaps are there, these types of curves are said to be discontinuous. So, a curve which is not having any gaps is said to be a continuous curve, and a curve which is having some gaps is said to be a discontinuous curve. Let us understand this in the mathematical sense. So, the definition of continuity tells that a function f of x is said to be continuous in the closed interval a comma b if for epsilon greater than 0 there exists a delta greater than 0 such that mod f of x minus f of a is less than epsilon whenever limit x tends to a, f of x is equal to f of a. So, this is what is the definition of continuity. And in this continuity definition, we need to remember the concept that we already know that it should be both left continuous as well as right continuous. And while using this definition in the mean value theorems, we are going to make use of one important property. So, that important property speaks that if at all, I need not to check for all functions, just I can simply say that a polynomial, trigonometric, exponential, and logarithmic functions are always continuous. So, we need not check this property, right? So, in this concept, we have seen the definition of continuity, and this is what is the definition of continuity at a point. That point, if I substitute, I should get this as limit x tends to a, f of x should be equal to f of a, and obviously we need to check whether it is left continuous as well as right continuous, and in order not to check all these conditions for a time, we have making a special note that every polynomial, trigonometric, exponential functions are always continuous. So, this is what is the concept of continuity. Now, let us see and go to the next concept which is called as derivable. We say that a function is derivable if it is derivable at each and every point on the given interval. That means I say that suppose f of x is a function which is mapped from a closed interval a comma b to r. This function is said to be derivable if a point c where this c belongs to open interval a comma b, then we can say that this function is derivable if limit extends to c f of x minus f of c by x minus c exists. And usually this is denoted by f dash of c. We all know it, right? So in order to check the derivability also, we are supposed to remember that it should be both left derivable as well as right derivable. So these are the basic concepts that continuity and derivability will be using in doing the mean value theorems. Now, let us see what mean value theorems are. There are basically three types of mean value theorems. There are three types of mean value theorems. The first mean value theorem is Rolle's mean value theorem. The first one is Rolle's mean value theorem and the second one is Lagrange's mean value theorem. And the third one is Cauchy mean value theorem. So, we have three types of mean value theorems. So, one is Rolle's mean value theorem, the other one is Lagrange's mean value theorem, the other one is Cauchy mean value theorem. Now, understand these theorems, each one of them separately. Now, let us start with the first theorem, which is known as Rolle's mean value theorem. For our easier sense, we will be denoting this mean value theorem as RMVT in a short form. Right. So, this Rolle mean value theorem states that let f of x be a function such that it should satisfy three conditions. The first condition says that f of x is continuous and obviously continuous should be in the closed interval as we have seen earlier. That is, it is a less than or equal to x less than or equal to b. Now, let us go for the second statement. The second statement states that f of x is derivable. F of x is derivable in the open interval a comma b. That means it will not include the values a and b. So, these two conditions are the conditions which are common in any of the mean value theorems. The only difference comes with the third statement in all the mean value theorems. So, this Rolle mean value theorem specifically tells that it should satisfy a condition if f of a is equal to f of b. If this condition is satisfied, then there exists a point C belongs to open interval a comma b such that f dash of c will be equal to 0. So, we need to make note of these 2 points. So, one condition is that it should be definitely satisfied f of a is equal to f of b. If this condition is satisfied, then f dash of c should be equal to 0. Now, we have just written the statements of the theorem. Now, let us understand this in the geometric sense. So now we see the geometric interpretation of Rolle's mean value theorem. That means we are just given the statements, now understand them mathematically. So this geometrical mean value theorem, this geometric interpretation says that f of x is continuous. That means whatever the curve I am taking, it should be definitely a continuous curve. So let me draw a figure which is having x-axis as well as y-axis. It should be a continuous curve. Let me take a curve which is of this form. So the first condition is satisfied. Let us go for the second condition. F of x is derivable. F of x is derivable means we should always understand that when f of x is derivable, there will be a unit tangent at each point of that interval. Now let us take that, suppose that there is a unit tangent at this point, right? So this point is nothing but A, this point is nothing but your B. So now this is what is represented on x-axis, this is what is represented on y-axis, which is B. If you observe, this part or this area is nothing but your f of A. Whereas if I go for this region, this is nothing but your f of B. And if you see here, we have started the curve and ended the curve at the same point. Why? Because it should satisfy the third condition. It should satisfy the third condition, f of A should be equal to f of B. We can have any number of curves, but the Rolle mean value theorem states that this f of A should be equal to f of B. That means they should be at the same height and same depth with reference to x-axis. They should be at the same height and the same depth with reference to x-axis. So this is a curve which is going like this. We may also take a curve which will be of this form also. So here this will be of this sense. So this is what is your x-axis and y-axis, and it is a increasing and decreasing curve. We can give a curve like this. Here also we can say that it is the curve which is at the same height and depth. And we can understand with the example. Suppose if I am taking a ball and throwing it up. So after reaching the maximum distance, what will happen? The ball will fall down. That means this is the point where it is falling down. That point is nothing but your f dash of c. So this is f dash of c is equal to 0. And we should always remember that in the Rolle's mean value theorem, this should be equidistant. That means this should be lying on the same line. And f of A should be equal to f of B. So now what we have learned from the Rolle's mean value theorem? So it should be a continuous one, it should be a derivable one, and it should be satisfying the third condition, f of A equal to f of B. Then obviously f dash of C is equal to 0, and we have seen it with the geometrical interpretation by drawing this figure. So this is what Rolle's mean value theorem is. As we have seen the Rolle's mean value theorem, now let us understand the applicability of it by solving some problems. So let us solve a first problem which simply states that verify, I am using RMVT for a short form, Rolle's mean value theorem for the function f of x equal to x square in the interval -1 less than or equal to x less than or equal to 1. So this is what is the function which is given. We need to verify the Rolle's mean value theorem for this. Let us start with the solution of Rolle's mean value theorem. So what is given? The given function is f of x is equal to x square. The first condition I should verify is whether it is a continuous function or not. So I observe that this function f of x is polynomial, right? You will be answering in your homes. So f of x is a polynomial, right? So if f of x is a polynomial, and obviously I have given a note point that this function will be always continuous. So f of x is equal to x square is continuous in the closed interval -1, 1. So the first condition is verified. Now let us check for the second condition whether this function is derivable or not. So the function is f of x is equal to x square. If I find f dash of x, this is nothing but 2x, implies I can say that this function is derivable. So f of x is derivable in the open interval -1, 10. Right? So the two conditions are satisfied. If these two conditions are satisfied, we are supposed to check whether it satisfies the third condition. What is the third condition? The third condition tells that f of a should be equal to f of b. So what is a here? A is nothing but -1 and b is 1. Right? So let us check. I substitute f of -1. So this is -1 square. This is nothing but equal to 1. Whereas f of 1, if I take, this is 1 square. This is also equal to 1. And we have found out that here this is f of -1 is equal to f of 1. This condition is satisfied. If this condition is satisfied, then I can simply go for applicability and check the condition f dash of c should be equal to 0. So let us see f dash of c whether it is equal to 0 and whether c is lying in between or not. And here we have seen that f dash of x is nothing but 2x. So f dash of c is nothing but, we know that f dash of x is 2x. So f dash of c will be nothing but 2c. 2c we equate that to equal to 0, implies we get the value of c as 0. That means at this point c equal to 0, this should lie between -1 and 1. And we observe that this point is lying between -1 and 1. And so definitely we can say that it is satisfying all the three conditions. Therefore we can say that f of x is equal to x square satisfies Rolle's mean value theorem. And suppose if any of these conditions are not satisfied, we say that Rolle's mean value theorem is not applicable. So we should get a point which is lying between a and b. Right. So we have solved one problem based on Rolle's mean value theorem. Let us see one more problem based on this Rolle's mean value theorem. So this Rolle's mean value theorem, if f of x is equal to 2x cube plus x square minus 4x minus 2, verify whether it satisfies Rolle's mean value theorem in the interval -√3, √3. Right? I think you have got a very clear idea about all the concepts. Now we will be doing it a little bit fast. So this is f of x is equal to this one. This function, we see that it is a polynomial, implies f of x is continuous in the closed interval -√3, √3. So the first condition is verified. So the second condition, it should be derivable. Let us check what well. So f dash of x. F dash of x here, if I take, this is 6x square plus 2x minus 4. So this is a function which is derivable. I can say that f of x is derivable in the open interval -√3, √3. So let us check the third condition. Third condition means I should check for these two whether f of a is equal to f of b or not. So f of -√3. So just simply substitute in this one. So 2 into -√3 cube plus -√3 square minus 4 into √3 minus 2. So this one, after doing the calculations, what I will get? Minus 6√3. This is plus 3. This is plus 3 and this is plus 4√3 and this is minus 2. If I calculate these two, you will be getting this as minus 2√3 plus 1. Right? Now let us check what is f of root 3. So this f of root 3 is nothing but 2 into root 3 cube plus root 3 square minus 4 root 3 minus 2. So this will be 6 root 3 plus 3 minus 4 root 3 minus 2. This is nothing but 2 root 3 plus 1. And if you observe here, you are getting f of minus root 3 as minus 2 root 3 plus 1 and f of root 3 as 2 root 3 plus 1. So, we observe here that f of minus root 3 is not equal to f of root 3. Therefore, as the third condition is failing, we say that Rolle's mean value theorem cannot be verified for this function. So, now let us go to the second mean value theorem. The second mean value theorem is Lagrange's mean value theorem, right? So in this Lagrange's mean value theorem, I have already said you the statements will be same as your Rolle's mean value theorem, only the third condition will be varying. So we simply say that f of x, let f of x is a function such that first condition is f of x is continuous in the closed interval a comma b, and the second condition is f of x is derivable in the open interval a comma b. The third condition will vary. Here the third condition says that there exists a point C belongs to open interval a comma b such that f dash of C will be equal to f of b minus f of a by b minus a. So this is what is the statement of Lagrange's mean value theorem. Now understand these statements with a diagram. So this is what is your x-axis. This is your y-axis. Let us take a curve which is like this, right? So this is geometric interpretation of Lagrange's mean value theorem, right? So the first condition is it should be a continuous curve, second one is derivable, so let us check that one, and the third condition I should see for this one. So let us mark this point as A, this point as B, so this is nothing but your A, so this is nothing but your B. So this distance is nothing but your f of A, whereas this distance will be your f of B. Now this is the line. So let me take a tangent at this point. So I will take like this. This will be the theta. This will be your opposite side. This is your adjacent side, and this is your hypotenuse. Right? So f dash of C is nothing but this will be the slope, and slope we know that it will be represented as tan theta. Tan theta is nothing but opposite side by adjacent side, where we see that this distance is nothing but your b minus a. So this distance is also b minus a, and this distance is there. This is f of b minus f of a. Right? So let me mark a point like this as P. So the opposite side is nothing but BP by AP. Right? So what is the value of BP? BP is nothing but f of B minus f of A, and the adjacent side is nothing but B minus A. So we have verified the third condition also. So the third condition states that if you are drawing a tangent at that point, that tangent should be equal to the chord joining these points. So this is the tangent and this is the chord. So this is the third condition which is referred to and we have proved. Now let us prove the Lagrange's mean value theorem by doing a problem. Let us take that, let there be a function f of x which is nothing but log x base e. We are supposed to verify Lagrange's mean value theorem in the interval 1, e. Right? So, here we observe that the given function is a logarithmic function. So, the logarithmic functions are always continuous. Therefore, I can say that f of x is a continuous function, is continuous in the closed interval 1, e. Now, let us check the second condition. The second condition is nothing but, here it is f of x. So, the derivative of log x will be 1 by x. Right? So, here we can see that f of x is also derivable in the open interval 1, e. Let us check the third condition. The third condition simply says that f dash of c should be equal to f of b minus f of a by b minus a. So, f dash of c. So, I substitute here 1 by c will be equal to f of b. The value of this is a, this is b, this is f of e minus f of 1 by e minus 1. Right? So, this one f of b minus f of 1 by e minus 1. So, this is 1 by c is equal to, if I substitute this one, so this is log e base e minus log 1 base e by e minus 1. And we know that log e base e is 1 and log 1 is 0 by e minus 1. Simply we can see, if I get it to the top, my value of c is e minus 1. And if you observe, obviously this value of c equal to e minus 1 definitely lies within this interval. So, this c belongs to open interval 1, e. Therefore, all these conditions of the Lagrange's mean value theorem are satisfied. Therefore, we say that f of x is equal to log x satisfies Lagrange's mean value theorem. Now, let us see the last theorem, which is Cauchy mean value theorem. Cauchy mean value theorem. This Cauchy mean value theorem states that here, there we are using only f of x, but here in this Cauchy mean value theorem, we will be having two functions, f of x and g of x. Right? So, this f of x and g of x, here the first condition states that if f of x and g of x are belongs to closed interval a comma b, then f of x and g of x should be continuous in the closed interval a comma b. In the same way, the second condition tells that f of x and g of x should be derivable in the open interval a comma b. And the third condition states that here g dash of x, if you are finding if it is not equal to 0, then there exists a value c belongs to open interval a comma b such that here this will be f of b minus f of a by g of b minus g of a. This value should be equal to f dash of c by g dash of c. So, this is the third condition which is varying in the Cauchy mean value theorem. Observe that f of x and g of x should be continuous, should be derivable, and if g dash of x is not equal to 0, this is the third statement that we have to see. Now, let us see the geometric interpretation of Cauchy mean value theorem. So, the geometric interpretation of Cauchy mean value theorem, let me take this as x-axis, this as y-axis. Let me draw a curve something like this, and this is a point called A, this is a point called B. If you observe, I am going to take like this. Here you can draw a tangent. Here, this is nothing but, this point is nothing but A comma, f of A comma, g of A, and this is nothing but f of B comma, g of A. So, this is the point where it is C. C is nothing but f of C comma g of C. So, we observe that this tangent is parallel to the line joining the points. So, this is the inference that we get from Cauchy mean value theorem. So this Cauchy mean value theorem, this is the third condition. So this condition is simply verified by geometric interpretation. And we also say that this Cauchy mean value theorem, from this Cauchy mean value theorem we can define the Lagrange's mean value theorem, but we cannot do the same with Lagrange's mean value theorem. And also we are supposed to know that here this Cauchy, we cannot guarantee that there will be existence of these kind of tangents for all the curves. Now let us verify Cauchy mean value theorem by solving a problem. So let us take f of x is equal to e power x given and g of x is equal to e power minus x. We need to verify that c is the average value which is lying between the closed interval a comma b. So we see that here f of x and g of x are exponential functions. So always we can say that exponential functions are always continuous. Therefore, the first property is verified. Now, let us come to the second part, which is derivable. So, derivability reads that f dash of x is equal to e power x and g dash of x is equal to minus e power minus x. So, we say that f of x is derivable in the closed interval a comma b. Now, let us check for the third condition. The third condition is f of b minus f of a by g of b minus g of a will be equal to f dash of c by g dash of c. Let us substitute. So this is e power b minus e power a by e power minus b minus e power minus a. So this is equal to e power c by minus e power minus c. Right? So after these calculations and all, so we will be simply arriving at this is e power 1 by e power b minus e power a by 1 by e power b minus 1 by e power a. So this will be equal to minus e power 2c. Right? So if I calculate this, we will be simply getting e power a plus b will be equal to, here also we will be getting a minus sign. If I take it to the top, here this will be equal to minus c. So as the bases are same, I can equate the powers. So this is 2c is equal to a plus b. So this value of c is equal to a plus b by 2. So this is nothing but the average value. Therefore we say that c also lies between a comma b. So this is Cauchy mean value theorem is verified. Let us see the application of all these theorems. So there are many different applications of this mean value theorems. So one important application is, suppose if you are moving by a car from one place to other place, suppose a gun 1 is there here and gun 2 is there here. This distance should be covered with a 60 km speed, we can cover in 1 hour. Suppose you are moving in this direction. If you are moving from here to here in less than 1 hour, means you have violated the speed parameter 60 km per hour. So obviously what will happen? The traffic police will issue a challan to you, and this is the main application of mean value theorems. So there are many different applications. One of the important application is this one. So in this session we have covered definitions, mean value theorems and its applications. I hope you have enjoyed my session, and stay home, stay safe and don't stop learning. Thank you.